Okay, good afternoon, people. Welcome back. I hope you had a good break. So today is going to be the last lecture. Think about it as lecture that you're responsible for it on the midterm. You're responsible for everything and anything that I've done. And by Wednesday, I will send some additional, maybe helpful instructions on what to look out for. Now, you know that your test, your midterm is on Saturday. You have to write it in your own section unless otherwise agreed to. And I haven't had any inquiries, maybe one or two that we responded to. And I sent you a sample test, sample midterm, although that midterm is from 2 years ago, where there were 5 problems involved. Now you're going to get only 3, and you have 2.5 hours to do. But you're responsible for everything that I've done. In other words, the test that you're going to get may not be the test that your friend gets in the other section. You may get an assembly, he or she may be getting a hybrid, or the other way around. Okay, he may be getting a beam, you may be getting a shell. Okay, so you should be prepared for everything that we have done. Now, the other thing is, tomorrow I have a lecture with you guys. This is your lab. I have a lecture with you guys tomorrow at 4 o'clock. In that lecture, I will send a second sample test. And my plan is to spend part of the lecture tomorrow to do some of those problems, because there's only 50 minutes that we've got, and I've got 5 problems for you as a new sample test. And the remaining thing is going to be in your final lecture on Wednesday, not Wednesday, on Friday, July 2nd, okay? July 2nd, the day before the midterm, I will do whatever is left over from the sample test, and I'm going to be distributing tomorrow. Okay, well, first of all, and remember, you have a homework to turn in by Wednesday at noon. You have that buckling problem to turn in by Wednesday at noon. Do you have any questions before I do the final item that you're responsible for at this point? Are there any questions? I'm assuming you can hear me. If not, somebody would have said, at least sent me a message by now. Okay, let's move on. So what we like to do is talk about free vibration of a structure. In this particular problem, I'm going to be concentrating on free vibration of a simply supported beam, and it's coming from chapter 22, but there are some modifications. Okay, there are some modifications. Okay, first of all, why do we have to worry about free vibration? Okay, but what is free vibration? That's good. So what happens, this last answer is probably the best one that I saw. So here's the situation. If you take this structure, think about it as a ruler, and take the middle point and move it down. Move it down and let it go. Assuming that it's an ideal world where there's no damping involved, this ruler will go up and down, up and down, in all likelihood in this mode. In other words, think about the long, slender ruler, simply support it, or you can think about it as pin, it doesn't matter, and pull it down and let it go. This will go up and down and up and down and up and down at a certain frequency. There is no force applied. The only thing that you did is you apply the force to move it off balance, basically, and then let it go. That is what free vibration is. Okay? Now, in real world, that will not go indefinitely. At some point, it will stop. The amplitude of this going up and down gets smaller and smaller, and that's because there is damping involved. We are not living in an ideal world. Okay? But free vibration assumes that there is free undamped vibration, means that there's no damping, and move this thing and let it go. By the way, it doesn't have to go like that. If you arrange things so that this end, of course, is pin and this end is pin, the middle point stays stationary, and you move this side up and this side down, then it will also vibrate, free vibration, but at a different mode. It'll go as a full sine wave. The simplest one is the half sine wave, like this. And at that frequency, it will vibrate like this. If you had a initial arrangement so that it was a full sine wave, and then let it go, it's going to vibrate indefinitely in that shape at a different frequency. Now, free vibration, one of the reasons that we want to know about this frequency, not that much the mode shape right now, but why is it that we want to know about this frequency? It vibrates at that frequency. Can somebody tell me why is it that we are interested in that? We know what it is now, but why is it that we want to know that frequency? What do you say? You're seeing
resonance at that frequency?
That's very good. Yes, because if you had a motor sitting on this, a rotary, a compressor or a fan or something like that, and it turns at a certain RPM, okay, and that RPM, that frequency matches the first natural frequency of this, then it will cause resonance. You're absolutely right. So we want to avoid resonance. There are other reasons, but the most common one that people should know is to avoid resonance. That's correct. Okay. Now we'll solve this problem for you, but I can assure you that finding that frequency and the mode shape using solid elements is killing a fly with a cannon. Okay, you already know, if you had a problem like that, what kind of element you should be using. Okay, you should not be using, for a problem like this, to find the frequency of vibration, you really should not be using solid elements. Okay, you can, but it's not the most appropriate element. You can use shell element, but it's not the most appropriate element. Beam elements is the most appropriate element for this problem. Okay, now it used to be that vibration was a mandatory course. I don't think it is anymore. So it's an elective, I believe. That's a bad idea. But anyways, these concepts were used to be discussed in a vibration course, first vibrations course. But I don't know where you pick those up. Probably in different places. That's bits and pieces in different places. Okay, now. I will do this thing as with solid elements, though. Okay, if there is time, I will go and do it with beam element. We'll see. But the issue of this simple support, first I do it the most common way that you know. Okay, we can do that, and then I'm going to show you a different way. Well, first of all, before we do that, by the way, there are some analytical expressions that, depending on the cross-sectional area, moment of inertia, and Young's modulus, etc., you can estimate it and then compare it with finite element results. But I'm not going to worry about that. Okay? In a problem like that, if you ever confronted it in a work environment or for your design problems, and I don't know, capstone design, you should not be using finite element. There are analytical expressions for this. Okay. All right. Are there any questions before we move on and doing this problem? No questions. Okay, let's move on. So I'm going to start with a part file because you can only do vibrations of a single part. If you have an assembly, you try to find natural frequency of vibration, it'll immediately tell you, I can't do it. Because what is important is resonating a particular part within your structure, okay? Not the whole structure. You cannot do the whole structure. You cannot talk about natural frequency of vibration of an assembly. That is meaningless. Okay, so I'm going to start with a part, and immediately File, Save Management. You should be the master of these for your test on Saturday. Okay, on a desktop, new folder, vibration, Lab 53. Okay, and let's go make it. So on a convenient plate, I'm going to make a three-dimensional object, which is 1 inch by 1 inch in cross section and 10 inches long, to be consistent with what is done in the book, although it really doesn't matter. So there we are. And let's make it 1 inch by 1 inch. Okay. Exit. And pad it by 10 inches. Now, a couple of things. You already know that when it comes to buckling that we discussed last week, you still have homework to do. You should not use symmetry. You should not take symmetry into consideration, because if you take symmetry into consideration, you may skip certain loads which are lower than what you predict, and in fact, it can buckle out of plane, for example. The same thing with natural frequency. You can use symmetry. For example, you can take only a quarter of that, not actually a quarter, yeah, a quarter of that, because you can cut it along the length, and in the direction X, that'll be 1/4, okay? However, if you do that, you will lose certain frequencies that may be critical, and you don't want to do that. Unless you know exactly what you're doing, don't use symmetry in buckling or natural frequency calculation. Okay, so apply material. Let me move this thing out of the way here. So make it a little bit up. Okay, apply material. We're going to make this thing out of aluminum, metal, aluminum on that part. And we say okay. And we're going to save this. And then we're going to go to, we're done here. So we're going to go to, what is this? A generative structure analysis. CATIA immediately sees a solid object and it meshes it for you. Now, is it important to be worried about the size of these things? Yes, if they pay you for a living. If you're doing this thing that your signature or your name as the design engineer for this particular project is important. It is important, but not for this course. In other words, linear, parabolic, unless we absolutely tell you to use parabolic or linear with a size given, such as your last homework assignment. I said use parabolic with that size, okay? You just go ahead and do the linear one, okay? And even for the linear, don't put a micron for the size of this object, because there's going to be a million elements there. You're going to sit there forever in order to finish the problem. Okay, I'll keep this. Now, obviously, the bigger it is, the less accurate the results, the less accurate the frequency, etc., etc. All right. Now, let's save the analysis. File, save management, save analysis. This is the right folder, Vibration Lab 53, right? And analysis, I'll just keep the default name. Remember, at the end, when you're done, you can quickly and efficiently change all of these names so that at the beginning, it starts with your ID number, your last name, and then whatever identifier you gave it. Okay, you can do that as you go along, or you can do that if you're comfortable at the end and do this. Now, we want a simple support at these ends. Now, one way of thinking about simple support is this be on a pin and this be on a pin, or this be on a roller and this be on a pin. You might say, well, what's it? Aren't they different? In other words, if you have a pin here and a pin here, would it be the same as a pin here and a roller there? The answer is, in the context of linear analysis, the answer is yes. But if this deflection was a lot, which is not in our case, and this was a pin, you know that there's going to be a force developed in this structure. That's common sense. I mean, if this deflection and a lot, this pin will be pulled in. That pin, if it was a pin, it will be pulled in, and of course there's going to be a force, net force developed in the beam. But in the case of linear analysis, that is not the assumption. In other words, these displacements are so tiny that there is basically no displacement, no force in this direction and in that direction. Of course, if there's a roller, there's no force. You know that. Okay? Now, so we're going to try to emulate this exactly like it is. Let's see now. Oops, where is this? All right. So this end, this bottom end, I decided to, well, clamp. Okay, it's really not clamp, because if this is free vibration, this can actually shrink in that direction. There's a difference. You know how they do simple support in real life? This is not how they do simple support in real life. They don't pin it here. What they do, they put a roller a little bit to the right and a roller here a little bit to the left, and then let this thing sag on that roller. They don't pin this. Okay? In fact, the three-point bending test that you do in a lab, if you want, for concrete or for I-beam, etc., they don't have this configuration. They take a sample, put it on two cylindrical surfaces here, cylindrical rods, basically it becomes your roller, and then load it. Okay, but when you do problems, when you did problems in deformable bodies, in mechanics, etc., you assume this was a pin. Okay, so I'm going to do the same thing, except that, let me be a little bit, okay, let's try it. Let's try it. Clamp. There we are. Okay. And on this face, I will not let it go up or in the direction X, but I will let it go in the direction Y. This is an approximation to what you're trying to do, a simple support. Remember, a simple support means that you put the structure on two cylindrical rods and load it vertically, okay, for example. That's not what I'm doing. When I clamp it, basically I'm saying that these 2 points cannot move at all with respect to each other, okay? Now, here we said that, okay, we're not going to let it move up and down. That's Z. And I'm not going to let it move in the direction X, okay? But I'll let it go in the direction Y so that it can actually do this if it wants to. It won't do it for linear analysis, but in real life, that's different. Good, good. Okay. Now, save everything.
Professor, can I see
Yes.
the coordinates? So, because like it's hidden between one of these toolbars. Because you restrain translation on 1 and 3, but I don't have visual what are the axes are.
Okay, so
It's behind the
this
model
direction.
manager.
Okay, wait a minute. What is the issue? I'm sorry, can you repeat that?
Oh, and actually, Cooper made a good point. I was not able to see the coordinate system, but now I can see it at the bottom right corner.
Okay, all right, good. Okay. All right, good. So notice that when I went to the analysis, it asked me, is this a static analysis? And I said, yes. But this is not a static analysis, okay? So let me guide you there again. Let's do it again. All right, so let me close this. Let me close that. Try it again. You see, you go to Start, Generative Structure Analysis, right? And recklessly as we have done in every other problem, except for buckling perhaps. Well, actually, buckling requires a static analysis anyway. I just left this thing as it is, static analysis. This is not a static analysis. Now, I can do a static analysis, but when I'm done, then I have to insert a frequency analysis. But if up front, we know that this is not a static analysis, let's do a frequency analysis. Notice there is two things here. There's a frequency analysis and there is a free frequency analysis. These are the same thing, except that for frequency analysis, you put some restraint. For free frequency analysis, you don't put any restraints, as if this guy was out in the outer space, not attached to anything, and we are expecting to see vibration frequencies of it. If this was in outer space, floating, then you can do free frequency analysis. But if this is a beam, for example, attached to, I don't know, this is the roof of your house, okay, it's attached to something, okay? So you're going to put some restraints there. So don't do free frequency analysis, do frequency analysis. You see, it no longer is static analysis, and when I click on it, we get a frequency case here. Now, I could have deleted that static, right-click delete. I could have deleted it and then done insert a frequency case if you want, okay? But since I knew what I was planning to do, as soon as I got there, I said, hey, don't give me the static because I'm not doing the static analysis. Just give me the frequency analysis and I'm on. So let's go ahead and do that. Clamp right there, there, and this is what I did. I selected this edge. Does not move in the direction X, does not move up and down. See that? Does not move up and down. Yep. There we are. Okay. Now we did let it move sideways. Like that, because we didn't put any restraint on it. It can move in direction Y, so it's consistent with this drawing. Okay. All right. Good. Let me save this thing. File, save management. Remember, I already saved an analysis there, which I didn't want to. So I'm going to say save as, same name, overwrite it, basically. That's okay. I could have kept the original one too, because it's totally useless. Now notice something, that there is no load. You can't apply any loads. Because this is, when you say frequency vibration, frequency's case means that it's a free vibration. Free vibration, you don't apply loads right there. We can't even if you wanted to, you can't do it. Okay? If we had gone the first route, in other words, did a static case first, and then inserted a frequency case, you will notice that when you're in the static case, these are active. But as soon as you're done and you move to frequency case, this becomes dim. So it's not surprising that this is dim, because this is the free vibration. Free vibration means no force. Okay. Guess what? This is it. Run it. Done. So let's look at the deformation modes. To see the deformation, this is what you always click. Ooh, that looks good. Now double click on this either on the screen or from the tree, either way. Double click on that, either here or there. You have an occurrence tab. Occurrence tab is because we have deformation at different frequencies. These are the modes and these are the frequencies. We never had this occurrence tab before. We had it there, but if you selected it, there was probably nothing there. But it says that at this frequency, 866, or almost 867 hertz, it will vibrate up and down like that. If you go to the next frequency, whoops, it goes out of plane. You see, goes out of plane. And other modes. This one is torsion. You can see that this torsion about that. Now, this is again. Some of these are in plane. So the first one is definitely in plane. Let's actually, what we do is let's look at the view from the side. There we are. And if you animate it, you can see that it stays in that plane, in plane. Okay. Let's look at another one. This is definitely out of plane. You can see that. This one is also in plane. Let's see from the side. Yep. This is that full sine wave. Remember, I said that you can arrange it, but at a higher frequency. So in order to resonate this, you need a fan that turns at a lot higher speed than your fan that resonate, make it go half sine wave up and down. Okay. This one is probably up. These are, let's see now, these are out of plane. Obviously, you can see that. Torsion. What is this? This is another in plane. You can see that. Obviously, these are all out of plane. It's all kind of weird thing. This is the most critical one. If you hit, if the fan hits that RPM, converted to hertz, this guy starts wildly oscillating. If there is no damping, eventually it'll go to, you know, basically eventually it'll fail. Okay. Eventually will go, the amplitude goes to infinity and it fails. The reason in real life it doesn't fail like that is there is a damping. This is a damped, undamped free vibration. Okay. Are there any questions at this point?
Yes. Which one would we select to be the most significant, or the one that we should take into consideration?
Okay,
Out of
so
all,
let me ask you that question. So let's look at these different modes and pretend that this is an I-beam, okay, that is sitting on your roof, okay, from one support to another support, or I don't know, an I-beam that sits on your, at least these regular two-story homes, and they don't have I-beams on the top, they have an I-beam at the bottom. Have you seen it? The I-beam at the bottom in the foundation, there's one I-beam go from one end to the other end.
Yeah.
Have you seen it?
Yes.
Okay. Good.
Yeah.
You don't see it on the roof. But if it's a high-rise, it's a skyscraper and things like that, there are zillions of these everywhere. Now, and suppose there was a fan, there was a motor sitting on that I-beam in your house on that support. Okay, there was a big fan or a compressor sitting on that I-beam, for example, in your basement, and that fan has a gigantic imbalance. The reason that there will be a the reason that I-beam will be resonating is that the fan runs at that speed and there is an imbalance in it. If there was a perfect balance, then of course the fan will not do anything. But the fan does not have a perfect balance, and therefore it causes a tiny little bit of force vertically up and down, tiny little bit at that frequency. Don't you think that that's going to be dangerous? Because if this guy starts to vibrate up and down, you know, then it will never even get to these frequencies. It will fail right at that frequency if this was an ideal world. Agree?
But isn't it safe to be above or below the natural frequency?
Yeah, but you're right. But when you turn on the fan, and the fan goes, let's hypothetically the fan goes to, I don't know, 1,000 RPM. Okay, that's a big figure. 1,000 RPM. At some point, it starts from zero and it has to go through that frequency, is it not?
Yeah.
At some point, it'll go through that speed to get to 1,000, is it?
True.
That's where you have a problem. In other words, in real life, if you know that there is a frequency below the operating frequency, you better cross that very fast. In other words, your fan must go through this very fast to get to 800, 900, and 1,000 eventually. If the fan sits there for a while, then this is going to be a problem. You're absolutely right. Below or above. If it's below, no problem. But if it's above, you're going to cross this. And the idea is that if you ever cross a resonant frequency, make sure you program your device so that it doesn't sit there for a long time. Go through it very fast, one way or other. Or try to completely avoid it. Okay? Does that make sense?
Oh, definitely. And for the
Okay.
frequencies, the 3,542 and the 4,300, the torsional ones, are those realistic like shapes
No,
out of it?
no, no, no. Yeah, it is realistic as far as the shape goes, but the critical ones are the lowest frequencies. Okay, these are all garbage. You'll never get there. You'll never get to this or get to that,
Yeah,
etc.
that looks
But
very
they're
good.
there.
It's like,
Mathematically, they're there.
okay, okay.
Okay, and remember, I said that the resonance is not the only reason that you look at these. If you might say that, wait a minute, if this is garbage, why am I looking at it? Well, there are other reasons. They're not important in destroying your part, but if you want to do a dynamic response, you need these guys. These are garbage in the sense that failure will not occur at these. Failure occurs right here, but these are needed in order to do dynamic analysis in CATIA. These are needed. It doesn't mean that they're garbage. Garbage as far as failure, yes, the part will get destroyed right here if it was an ideal world. But these are needed to do dynamic response, forced response. You need these things, okay? In fact, there's a million of these. There's infinite number of these. Okay, can we move on? Any questions? Now, you can plot displacement, total garbage. Look at it, 82 inches. The whole thing was only 10 inches. 82. So these are magnitude means nothing. The magnitudes mean nothing. The shape is okay. Because the magnitudes mean nothing, the stresses mean nothing. So it tells you if it vibrated at that mode where the biggest stress is going to be, but you don't have to be a brain surgeon to know that, because you know that a beam, simply supported beam, has the biggest stress at the middle point. You don't have to be a second-year student that knows that. But these numbers are totally garbage, useless. The frequency is not, but these numbers are, because displacement are total garbage. Okay? It's so unfortunate that our students don't take a course in vibration. Very unfortunate. I mean, unless they decide to take the technical elective one. Good. So let's go ahead and move this and do this problem with a different type of element. Now, please notice that this gave me a first frequency 866 hertz. Okay. I can't bet on this. I'm not going to bet any money on that, because in order to have any confidence in any numbers that you see here, you must do proper mesh conversion studies. But let's keep that in mind, 866, because I want to repeat the same problem for you using beam elements. Are there any questions about this problem before we do it differently? Okay. So I'm going to kill this. And the reason I kill these is that when I do file save management, if these guys are on my screen, they're not killed, they're going to appear in the list, and it just causes a confusion. That's pretty much it. There. So I start with a new part file. Okay, and I'm going to immediately save it as file, save management, save as, same folder, but I'm going to give it a different name, model with beams. Beam model. Okay, because I'm going to keep the original one. I don't want to destroy that. Otherwise, it overwrites it. You see how dangerous it is when you overwrite your own work in your own folder? Okay. So let's create a line. So let's create a point first. 0, 0, 0. Right there. And a line. Point and direction. My point is right here. My direction is along the y-axis, because that's how I made the other part. Yeah. Along the y. And the length is 10. 10. Remember that guy was 10 inches long? Good. This is my model. This is my model. That's it. That's it. Let's apply I can't remember. Did I apply aluminum to? I think I applied aluminum. Let's apply aluminum to this. Aluminum. Metal. Aluminum. On this part. Say okay. And I'm going to save it. And I want to solve this thing as a beam problem. Okay? On purpose. I'm going to do some stuff. And then I'm going to ask you, what's going on? This is a good time to do it because you need this stuff for this beam stuff for Saturday. So we go to generative structure analysis. Frequency, right? Frequency analysis. You agree? Frequency analysis. I don't want to do static. I can, but why would I do that? See? Frequency. Notice that the loads are all dimmed, by the way. Now we're going to mesh this, right? We're going to mesh this. Agree? And how do we do that? Beam mesh. You need all this stuff for Saturday. Beam mesh. And I want to remind you that the reason it will not hassle me, I can do that, is because this was a line. Remember that? I created a line. If you have created this thing as a sketch, it will not let you pick it. And what would the remedy be if you created this line as a sketch and you tried to mesh? Come on, guys, you need it for Saturday. What do you say?
Join it.
Yes. If you did it as a sketch, it won't let you pick it. You'll have to go back and join it. Very good. Excellent. Okay. I don't care about the line. Look, this was 10 inches. Remember that? This was 10 inches. Why don't I make it 10 elements? How about that? 1 inch. Remember in the other one, probably I had 2,000 elements or something like that. You know how to get the hang of these. Okay, so it meshed it.
Professor, you just made the element size 10 inches.
Oh, really? So it's 1 element. Believe me, it's going to give me a good result. Still, it's going to give me a good result. Let's go back, fix it.
Sounds good.
Okay, so let's go ahead here. Let's make it 1. These beam elements are so robust, you can get excellent results with 2 or 3 elements through the length. Even in some cases, 1 element. But it's all right. I made it 1 now. I think I made it 1. What did I do? 1. Okay, so that's 10. Good. So what's the next step? Help me with that. What is the next step?
$3D
3D what?
I totally forgot. It's the model manager bar.
Yes. Here, which one?
That one. They're pointing at it right now. It's the box. Yeah.
This one. Is this a 3D model?
1D.
Ah, 1D property. Okay, next. Support, right? Support, yeah, right there. Okay, very good. It picked the proper material. Aluminum, right? Rectangular. We know it's rectangular, 1 by 1. We know that. Here, look, rectangle. Very good. Size, 1 by 1. I mean, ordinarily you get 0 by 0, you change it to 1 by 1. But I can't close it. What do I do?
Set orientation.
Yes, that means I need a point. And I don't have a point. I have a point here, but the point cannot be on that line. Even if I try to, it's going to come back and go nuts. See that? So I have to bite the bullet, go back to my part, create a point. Now that point cannot be on this line, cannot be on the continuation of this line. If it's a circle, don't worry about it. You don't need orientation point. But if it's not, then the point, there are many of them that I can pick. But and I suggested, when I was discussing these two, these things. I said that there is a process behind this thing, but I can't repeat the process every time. If you want, go and look it up. And I'm going to create a point, for example, at the coordinate here, y being or x being, I don't know, 2 inches, something like that. Totally useless, totally irrelevant, okay? But this allows me to orient the beam properly. Go back here, 1D property, support, size is correct, orientation point. Look, notice that it turned it around. It turned it around so it's exactly the way I want. Okay? Good.
I still don't see the point behind that point. Like, what is that point making for us?
What is the role of this point?
Yes.
Well, if you looked at what I did a minute ago, this was tilted. This was tilted. It was tilted. You don't want it to, this particular problem, I don't want it to be tilted. I want it to be like that, the 1 inch through the thickness of this. I don't want it to be tilted because the response is going to be different, okay? So the role of this orientation point is to make sure that this is oriented properly so that when you load it or you calculate frequencies, etc., it is what you want, okay? If it's a circle, you don't have to worry about it. Anything but a circle, you've got to go watch the videos. I told you this is not random. This is not a random point. This gives you the direction of x. This gives you the direction of y. And this is z. It has nothing to do with this. As soon as you think about that, you see that the role of this point is to make sure that the orientation y and z is correct with respect to this direction. Okay? All right. That is the role of this. If I change this into a different point up here, this will tilt. If it tilts, the beam doesn't tell you, but of course the response of the beam is going to be different. You don't put I-beam any way you want. You put I-beam in a very specific orientation. Okay. All right, good. So this is it. Now, restraints. This end was clamped. Remember that? Let me hide this. Make sure you hide that. Because the clamp goes not on the point, on this vertex. If you put it on the point, it'll take it for you gracefully, but at the end, it'll give you no deformation because there is no restraint, or it'll give you something that doesn't make sense. This one is on a roller, so user defined. That particular point does not move in y and z, but is free to move in the direction x. I'm just lucky that orientation is the same. I don't have to do this again. And you do not take symmetry into consideration because you'll miss frequencies. So let's save this thing. File, save management. No. Analysis, save as. I don't want to overwrite my old analysis. I want to say model with beam. How about that? Beam elements. Beams. Okay. Say OK. And say OK. And this is it. All you need is geometry, the restraint. Load does not play a role in free vibration. And you click on it and run it. Okay, let's look at our first mode. $1,360 as opposed to 800, as opposed to almost 900. Remember, it was 866 with solid elements. Okay, with solid. This is 1361. Okay, and if you say, well, wait a minute, this is quite a bit off. Well, first of all, I have absolutely no confidence in my original number, 866. I told you. Second thing is that what I did here, clamping here, this is not the same clamp as I clamped there, because there it assumed that that edge at the end where you clamp cannot change length. There is no such an assumption in beam bending. Okay. By the way, you notice that these two are identical. That's because one of them, this is one of them. Let's look at that from the top. Okay, this is the view from the top, which the beam comes out of plane like that. See that? It comes out of plane like this. And then it can also go out of plane in the other direction, direction Y. So two of these must be the same because it can have the same mode. Let me see that. Is this the one? No. Yeah, see, these things are coming in double because if you imagine a beam, it vibrates in, for example, the vibration response in the XZ and YZ is the same because you think about it. Just look at your geometry and look at the restraint. XZ and YZ, there is no distinction between them when you look at the way it's restrained. Okay. Yeah. So anyway, once again, you can plot the displacements. It's totally useless. 87 inches. You obviously in beams you cannot plot stresses, so that's okay. Now, one last thing before I stop for today is this: when you look at the problem done in the book, instead of me, let me see for a second. Instead of me actually clamping this bottom, for example, I use something called a virtual part and use these. Let me show you these things. Use these icons that we have never used before. The only thing that we have used out of this list is surface slider, but there are also pivots, sliding pivots, etc. Ball points, etc. So what I'm saying is that in the book, I've shown you a feature here that if you want, you can do it like this, and on the other side, you make it another pivot. This one can actually roll like that, but it can go up and down only. All right. So, are there any questions?
We didn't need to join in this.
No,
okay.
Because I drew it as a wireframe. I drew it as a line in space. Okay, but if you drew it as a sketch, you must join. You cannot measure.
Okay, and for homework 6, we had the buckling question.
Yes.
I did not mesh, and it was sorry, I did not join, and it all went through good. So this makes me a bit more confused about when to join and when not to join.
Well, we have done this thing many times.
Okay.
Go watch the lectures.
Okay.
When you draw a sketch such as that C, I don't know which you have to do the C one, that the folded sheet method, right? When you do the folded sheet method, when you draw the C and extrude it, you don't have to join. But if you draw a vertical line, extrude it, horizontal line, extrude it, another vertical line, extrude it, create that C from those three surfaces, you need to join. Or if you extracted the surfaces separately from a box, you have to join, but not with the extrusion that we did. And believe me, you go watch the videos, it's all there. And even if you don't watch the lectures, the homework, it's there. The homework on shelves and stuff like that. Any other questions? Now, what I'm going to do is I'm going to kill this session.